Hello everyone! In this video we're going to be talking about linked lists. These are what we would commonly call an abstract data type. And abstract data types are a big focus of CS1, but it's really helpful to kind of have a little bit of a background before you get there. So these are included as chapter 17 of our textbook. Now, the cool thing about linked lists is that they're dynamic. The length does not need to be known ahead of time. It can increase or decrease as necessary, and it doesn't require us to really monitor the length of our arrays the way dynamically allocated arrays would. Adding and removing items is really easy. Because we add things one at a time, we can add in one step usually. If we want to remove a specific item after we find it, it's really easy to remove. So the only hard part is finding it. Each individual part of a linked list is called a node, and those nodes do not necessarily have to be together in memory the way arrays do. If you have a one-dimensional array, every element of that array is stored right next to each other in memory, contiguously. Similar story with two-dimensional arrays, each row is stored contiguously, so all of those have to be next to each other. That's not true with linked lists. The individual node, each individual element of the list, can be placed wherever there's room in memory. This does make finding a particular element a little bit more difficult because we might be jumping around in our memory space from node to node. We don't keep the address of any particular node except for the first one. And the first one's going to lead us to all of the others. So in order to maintain all of the elements, a list of elements, each node has to have a link, hence a linked list. So each node essentially has two parts, a data section and a link section. So we'll have the information that we want to store in the data section, and then we'll have a link to the next node in line. That way, if we have a list, the only node that we have to keep track of is the first one. And since the first one is linked to the second one, we can get to the second one. Since the second one is linked to the third one, we can get to the third node, and so on down the list of elements. Here's a basic template for creating a linked list. This is done with structures and pointers. So we're going to have a structure. This one's called linked list node, or LL node. And remember, it's got two pieces. It's got a data section and a link section. So we've got a very simple data section in this case. The only data we're storing is a single integer. And the link is of type struct LL node pointer, and it's called next. So next points to the next node in line. And it's of type pointer because it has to point to that location in memory in order for us to follow each individual link to each node in memory. So we're going to go ahead and take this and start coding. We're going to put this in our program that we're going to build. This is just going to be all about linked lists. So each individual node has a data section and a link section, where the link is a pointer to the next node in line. So the pointer type has to be the same type that we are, struct LL node, and we've called it next. So that gives us the format for how we're going to create each individual element of the list. Then we're ready to start adding elements to the list. So we're ready to start adding nodes. There are three different options. We can add to the beginning of the list, we can add to the end of the list, or we can add in order. So for numbers, that most likely means numerical order, smallest to largest. And these are actually listed by order of difficulty. Adding to the beginning of the list is really easy. So that's going to be the first one that we do. Here's kind of a diagram to really visualize what's happening with the linked list. A list starts initially empty, and that's very important when we're dealing with pointers, to originally start with a null pointer, an initially empty list. So if we call it myList, we're going to start it at null. Okay, so here's our list. Our list is of type struct_ll node pointer. So that'll allow us to access the first location. And we'll start it out as empty, which means it should be equal to the null pointer. So null is an empty pointer, matches the data type of struct_ll node pointer, and we're calling it myList. Now to add nodes, if we're going to add to the beginning, the new node that we create is going to go at the beginning of the list, which means its link section should point to the rest of the list. So here's what we have at the moment. We have myList, which is currently null. It's empty. So we're going to create a new node. That means allocating space for it, and then point the new node that we've created to the rest of the list. So we're going to take its link section and point it to what myList is pointing at. Then we want myList to point to the front of the list, so we're going to modify that pointer so that myList is pointing to the new node, which is the new front of the list. So let's do that. Anytime we allocate space in a function, we're going to want to return a pointer, either to that space or to the head of the list if that space was created either at the end of the list or in the middle of the list. So we're going to create a function that will add to the front of the list, so it's called addFront. It's going to take in the current head of the list and the data that we'd like to put in our new node, and it's going to return a pointer to the front of the list after it's been modified. The first thing we're going to need to do is allocate space for our new node. Which means allocating space for it using our malloc function, which returns an unformatted pointer. So we're going to cast it to be of type struct_ll node pointer. And we want to allocate enough space to store something of type struct_ll node. Then we're going to set the data to be this input value that we got from our function. We're going to set the link part to be what was the front of the list. And then we're going to return the new head of the list, which is now temp. So we're doing all of the same steps that are shown here. We created the new node. That's here, where we allocated space for it, and then added the data portion. We pointed the link part to the rest of the list. That's this. And then we make the head of the list, this new node that we've created, by returning that to be our new head of the list. We're going to let the user provide values for us. And we're going to not specify how many values they're allowed to enter or how many we're expecting, just to keep adding values, and when they're done to give a -1. So they're going to give us a number that we're going to add in. We're going to update my list, so my list will now be equal to the list that's returned by add front when we give it the current head of the list and the number to be added. And then they'll give us a new number. Now, in order to make sure that this is working, we're going to need a print function. So we're going to create something that will allow us to print this linked list that we're building. Something that takes in the head of the list and is able to print all of the individual nodes that are in the list. So here's a quick example. The only thing that's really tricky about printing the list is we can't move the actual head of the list. If we move it, then we'll start losing nodes because we have to keep track of the beginning of the list. So instead, what we're going to do is create a helper pointer that we can start at the beginning of the list, and then we can change helper as many times as we want. So we're going to create this helper pointer, and we're going to set it equal to my list. So you can see both of these pointers are pointing to the beginning of this example list down here. It says as long as helper is not equal to null, print the data section of the node pointed to by helper, and then move helper to helper next. So let's trace through this real quick. Helper is equal to my list, so we point both of them to the same beginning of the list. Since this is not null, print out the data section, so print 1, and move helper to helper next. Well, this is where next is pointing, so we're going to move helper from this node to this node. And since it's not null, it's not empty, we're going to print 2, and then move helper to helper next. And since this one's not null, we're going to print 3 and move helper to helper next. In this case, the next link should be pointing at null, and so now helper is null, which means we should not continue the while loop. So let's use that to print our list. We'll create our helper pointer. And start it at the head of the list, which we've passed in as our parameter. As long as that's not null, we can print out the current value, which we're storing integers, so we'll print an integer, from the data section of where helper is pointing. And then move helper down the list using the next link. This is just a little separator that we're going to put between the user input and the list that we print so that we can clearly see the difference between the two. Okay, so it says enter integer values to be stored, end with a -1. We're going to enter just 3 values to start with. So here's 5, 3, and 7, and with a -1. And that's going to print out all of those numbers that we've stored in our linked list. One thing to notice here is that they're printing out in reverse order, and that's because we always add to the front of the list. So originally we started with an empty list, and then we added 5. That made our list 5 followed by null. When we added 3, we added 3 to the front of the list. So that made our list 3, then 5, then null. And then we added 7. So always adding to the front of the list, we have 7, then 3, then 5, then the end of the list. One of our other options is to add to the end of the list. Now, a lot of this will be similar to printing a list, which is similar to traversing a list. In order to add to the end, we have to first get to the end of the list. So adding to the end of the list is going to create a new node at the end. We have to start by creating the new node, which includes allocating space for it. Then we have to traverse to the end of the list. So we're going to create a helper that can go to the end of the list. Once we've found the one that has a null pointer for its link portion, we can make this the new end of the list by pointing this helper node to the new node that we've created. So that'll be our new end of the list, so we need to make sure that its link section is set to null, because that's how we find the end of the list. It's always when we get to the null pointer at the end. So we'll see this new version. This is adding to the back of the list, but the parameters are the same. We'll take in the current head, the data for the new node, and we're going to return the new head of the list once we've modified stuff. So now we know we need 2 pointers, one for our new node and one for our helper. I'm going to start by creating the new node. Which means allocating space for it. So we're going to call our memory allocation function, that's malloc, with the size of a struct LL node, which we know contains an integer and a pointer, and casting that to be of type struct LL node. We can then set the data section using the data from the parent function. And we're going to set the link section to be null, because this is going to be the new end of our list. If we're adding to the back of the list, this will be the new end. So we have to make sure that it points to null afterwards. We're going to set helper to be the head of the list, so that we can traverse the list to find the back of the list. There's a chance that the list is currently empty. So if the list is empty, then this new node that we've created is the only node in the list. Otherwise, we're going to traverse to the end of the list. So we're going to move through the list until we find the one that has a null pointer on the end, and change that so that instead of being null, it's going to be the new node that we've created. And then we're going to return the head of the list, which we've been careful not to modify. The head of the list remains the same. We use helper to traverse the list. The only time this is going to change is if it points to null, in which case the new node that we've created will be the one and only node of the list. So we're going to replace this function with our new one so that we can see it working. We're going to use largely the same numbers. So that we can see now that we're always adding to the back of the list, it's going to do our first number first, then our second number, then our third number. And then of course the end is a null pointer out here. Now we happen to have all of our numbers in order, but that's only because we added them in that order. They're not necessarily going to be in order if we don't add them that way. However, we can make a function that will go ahead and place them in order, which saves us the need to sort them later. This is adding in order. And of course, this is a little bit more complicated than either adding to the beginning of the list or the end of the list, because we actually have to find the precise location for our new node. So here's the steps that we're going to follow. We're going to allocate memory for the new node using our memory allocation function. We're going to determine where in the list to put the node. Now most often this means identifying the new nodes, the one that we created, the new node's predecessor. So that's the one that comes before it. Then we can point the new guy to the one that should follow it, and we can point the predecessor to the new guy. A lot of our work is going to be done here, determining where in the list to put it, because there's a bunch of options. It could be that the list is empty, which means the new node we've created is the only node in the list. It's going to be the new head of the list. It could be that the new node belongs at the front, which would be the same as doing an add to front. The new node could belong at the end of the list, which would be the same as an add to back, or that the node belongs somewhere in the middle. So here's an example. This is our current list, we're pretending. It's got two nodes in it. One has data 4, one has data 8. And we want to add something that has data 6 in it. So we know that this should end up with a list that looks like this. 4, then 6, then 8. So this belongs somewhere in the middle of the list, which means our first step is to allocate memory. We'll create this node, put data 6 in it. We're going to leave the pointer space open for the moment. We're going to find the logical predecessor. So that's the one that comes before the new node. The new node has 6, so the predecessor is the one that has 4 in it. So that we can take our new node and point its link section to the successor. So we want 6 to come after 4. So we're going to point 6 to where 4's link section is going. Then we're going to point the predecessor to the new node. So change this link so that it points to the new node. So that our new list now is 4, 6, and 8. So let's turn this into code. This will be an add in order. Parameters and return type stay the same. We're going to return the head of the list. We're going to take in the head of the list. And we're going to take in the new data that we want to put in the list. We're going to create a combination of pieces, some from add to front and some from add to back. We definitely are going to have to create our new node. So that'll be temp. We are probably going to have to traverse the list. There's a chance that the list is empty, and there's a chance that our node belongs at the beginning of the list. In both of those cases, we won't need helper, but for both of the other two cases, we will. So we're going to go ahead and declare it. We're going to allocate space for our new node. So create something of size LL node. We're going to set the data portion. We're going to start the link portion, this next pointer, as null. We can change that if we find out it's not going to be at the end of the list. So these are our primary steps. We're going to first check to see if the list is currently empty. And if it is, then the node that we created is the new head of the list because it's the only node in the list. Okay. Then we're going to check to see if it belongs at the beginning of the list. So we're going to compare the data portion of the list to the data that's currently in the front of the list, so that if the new data is less than, then it belongs at the head of the list. So temp next, instead of pointing to null, should point at head. And temp is the new head of the list. Otherwise, we need to find the location in the list where our new node belongs. So we've got to find the logical predecessor. So we want to find the node that temp goes in front of. So we need to find the first location where our current data that we just added is less than the data stored in not the current location of helper, but the next location of helper. So what we're looking for is the first point in time where 6 is less than one of these numbers. So we would be looking for, is 6 less than 4? No. Is 6 less than 8? Yes. So helper is the logical predecessor. So when we're looking at numbers, we're looking at helper next. If we find it, then we need to point the new node to its successor. So that's the one that we have here. So we'll point the new node to its successor. Point the predecessor to the new node. That's going to be helper. And then we'll return the head of the list. And if this is not true, meaning we haven't found the node yet, then we want to advance helper so that we can keep going. So if we haven't returned already, you can see each of our other checks results in a return. So if we make it here and we haven't returned, that means we need to add to the end of the list. And that helper next, which is currently pointing at null, should instead point at temp. Alright, so now we're going to run this one, and we'll see that it should put values in order numerically. We'll go back up to main and swap add to the end of the list for add in order. And now we can enter all of our values. To see that when we print the list, even though we entered them out of order, they're now in order from smallest to largest. Now we've been allocating a lot of space for our linked list, and we've not freed any of that space yet. So that is something that we will need to do, as it's our job as the programmer to free any space that we allocate for our data structures. But I'll save that for the next video. See you then!